Now we want to look a little more closely at what goes on in this bottle engine. In an experiment that we did, we raised the water by a distance of 1.11 meters and measured how much water we got out of the system at that altitude. In order to accomplish that, we had to add enough thermal energy to raise the pressure by 11,000 pascals, 11 kilopascals. The rho GH here is your 11,000 pascals. Pressure is atmospheric, which we round off to 100,000 pascals. Velocity is 0. Going to use Bernoulli's equation. Comparison with what we have down here shows us that the pressure down here has to be 111,000 pascals, or 111 kilopascals. We're assuming a volume of 2,000 milliliters, and we want to know what the temperature has to be to accomplish that. We get that temperature fairly easily. We started from a state of 100,000 pascals, temperature 1 of 297 Kelvin on this particular day, and a volume that's equal to the volume, the 2,000 milliliter volume we had here. There's no change in volume in this first part of the cycle. Formally, since PV equals nRT is constant, and V and N are constant, R of course being a universal constant apparently, we see that the pressure temperature ratio is constant, which means P1 over T1 equals P2 over T2. Then using temperature T1 297, pressure P1 100,000 pascals, pressure P2 111,000 pascals, we can easily determine T2. Solving this relationship for T2 and plugging the numbers in, we see that T2 has to be, well, the pressure ratio is 1.11. Original temperature was 297, so that we get approximately 330 Kelvin. I accidentally wrote 230 there, but that's supposed to be a 3. So it's really 330 Kelvin, which comes out about 57 Celsius and compares very well with the temperature that we observed from the thermometer in the bottle. Now, we had water that was capable of raising the temperature of this system to 80 degrees Celsius, or 353 Kelvin. After raising to 57 Celsius, the altitude is going to remain at 1.11 meters, and therefore the pressure is going to remain at 111 kilopascals. Pressure is not going to change. We can still increase the temperature from 57 to 80 Celsius, a difference of 23 Celsius, or 23 Kelvin if you prefer. Kelvin maybe is a little bit more appropriate. That's going to entail an expansion of the gas, and as the gas expands, it's going to displace water out of the bottle. The only place the water's got to go is up the tube and into the reservoir, so we're going to be able to determine how much water should have been raised into the reservoir at the height of 1.11 meters. Okay, so number of moles remains constant. Temperature and volume are going to be changing. Volume over temperature is constant since the number of moles and the pressure remain constant now. Remember, the pressure remains constant because the altitude of the water in the tube remains at 1.11 meters. And this implies that our ratio of volume to temperature at state 1 is the same as at state 2. So that volume at state 2 is just the temperature ratio times the volume at state 1. And that allows us to very easily determine volume 2. Volume 1 was 2,000 milliliters. That is, we started with 2,000 milliliters of air in the bottle. The temperature ratio is 353 to 330 Kelvin. And we then determined that volume V2, this ratio is about 1.07, gives us about 2,140 milliliters. That implies a volume change of 140 milliliters, or 140 milliliters of water raised to a height of 1.11 meters. That compares pretty favorably with what we observed, which was, I think, a little lower than that, around 110 milliliters. From that information, we can determine how much work was done, or how much potential energy the water actually gained. Then we want to go to the idea of efficiency, which is going to require us to know how much thermal energy, delta Q, had to be added to the system in order to increase its temperature. We'll be comparing the potential energy gain of the water with the thermal energy that had to be added to accomplish that gain.